So the first important thing is exam 2 is a week from today. So that's Tuesday the 11th. And the topics. So first of all, it's all the stuff that we covered up through exam 1. So remember, it's cumulative. So you need to spend some time going back through those old problems. I'll talk about how to approach that in a second. And second, you have to be able to do problems like those vector practice problems. And then third, you have to be able to do problems like the 2D kinematics of a particle. And that's all. So we'll just stop there. And we're done with all that stuff now. So you have a week to let this stuff soak in. I'm going to go on to the new topics. So far, we haven't, like, this is going to be the first test where you've had to go back and do old stuff, revisit old stuff to get ready for it. What I would recommend doing, I mean, the more time you have to spend on the old stuff, the better, obviously. But I think a good approach would be go back to those problems, look at the question, ask yourself if you know how to do it. Like, do you know the approach? Do you remember the approach? If you do, then there's no need to spend too much time on it, you know? If you don't, that's when you should take some time to remind yourself the process of doing that kind of problem, okay? And hopefully that'll save you some time as you go through the old ones. Anybody have any questions about the test? So remember, the tests are just based on those practice problems. There's no short answer questions about the lectures. It's just doing problems. And I think I would say you know you're ready for the test when you know every problem well enough to like explain how to do it to someone else. If you understand why every decision was made along the path of doing the solution, then the test is going to be straightforward. Okay? You won't see any questions that surprise you or anything like that, I don't think. Any questions? Okay. The lab exams are going slowly, so I need to get those done, but I'm probably like a third done so far. So I probably won't get them back to you this week, but I gotta get them done. So I know you want them back, and I want them off my desk. All right. Does anyone have any questions about practice problems or example problems? Anything you'd like to see me do before I go? So what I'm doing today is going on to the next topic that's not going to be on the test. So if you have any questions related to stuff on the test, I'd be happy to answer those questions for a while. Anyone struggling with any homework problems or anything?
Could you maybe just go over one more?
Sure. Oh, make up an example, like?
Sure.
Okay.
Yeah. Well,
Okay.
or is there one that requires both?
Yes, I'll do one that requires both.
It might take a long time, but
Okay.
it might be helpful.
Yes. Okay, so let's do one like that. So let's say a ball is thrown at 30 meters per second at an angle, let's say 10 degrees below horizontal. From a height of 3 meters. Ooh, let me do an example after this too. That's something just popped into my head. But so first, what's the elapsed time for the ball to hit the ground? How long until the ball hits the ground? And second, how far does the ball travel horizontally? Before it hits the ground? Okay, so what's going on here is that looks like a dinosaur. That's supposed to be a guy's hand. Why is his thumb so far back on his arm? I don't know. This picture is ridiculous. No, that's the like motion lines. And that's where he releases it from. And excuse me. He throws it like that, and that's a 10-degree angle. Okay.
It was a 10 degrees above the horizontal. I mean, below the horizontal, though, right?
Right. So that vector. So the dotted line is horizontal, and the vector is below. And the path of the motion starts out with a slope like that, and then follows a horizontal path. No, it starts out with a slope like that and follows a parabolic path. So the first thing we have to do is make those 4 choices. Time equals 0 is the instant it's thrown. I'll call it the instant released. Time final is when it hits the ground. And the origin location, let's put it on the ground beneath where it is when time is equal to 0, so beneath that release point. And I'll do the coordinate system like this. So the origin is on the ground. Beneath the ball's location at time equals 0. And the coordinate system has the y-axis up like we always use for free fall, and the x-axis horizontal in the direction of motion. So that's the way I have it drawn here. Now we can go through our list of things. Do we know time final? No, that's what we're trying to find. Do we know acceleration? Yes, it's free fall. So AX is 0. AY is negative 9.81. Do we know anything about the initial position? So what's the X component of the initial position? 0. Anyone have any questions about that? This kind of stuff can be a little confusing. So coming up with these components for the positions really is a vector problem. You can also think of it as coming up with the coordinates of that location in the coordinate system we've defined. So we're basically coming up with the coordinates of that star. And remember I said that that height is 3 meters. How could that be 3 meters? That guy is like, 3 meters is like 16 feet. How tall is that guy? He's got to be standing on something. Not realistic. And what's PIY? Yep, PIY is 3 meters. And then do we know anything about the final position? No. We don't know anything about the X,
Yeah, we know that Y is.
but we know that Y is 0. So PFY is equal to 0. That's how we know that it's on the ground.
And then would PFX tell us our answer for part B?
For part B, that's right, exactly. Do we know anything about VI?
Well, it's 30 meters per second.
Yeah, so that's what we're going to get from this vector. So we're going to use, so this vector has a magnitude of 30 meters per second, and it's in this direction. And so we're going to do a vector calculation to come up with those velocity components. Right. So,
And so the length, like where you would put the length is 30.
right, exactly.
Why?
So let me draw it over here, and I'll try to. Okay, so what we're doing, this is a picture of the velocity vector at that instant, the black vector. So let me draw it again here. It has a magnitude of 30. And if we put the tail of the vector at the origin of the coordinate system, that's the positive x-axis, that's the positive y-axis. We know that this angle is 10 degrees. And so this is just like a problem in the vector practice problems. To figure out the components of that vector, the initial velocity vector is the length times the cosine of this. What? It would be positive. The 10, you're right on the 10, but it's clockwise to get to the 10, so it would be negative 10. Or it would be positive 350 if you go the other way around.
Well, I understand what you're doing right now.
Yep.
And I now understand like that VI needs to be using the vector.
Yep.
But I was just wondering why the velocity, because like when you first introduced vectors, you just said that was the length, and so I didn't see how the velocity was the length of the vector.
Okay, so right.
That might just be a technical thing, though.
In a way it is. So these vectors are not, you can think of like these vectors don't live in real space. They live in just like a mathematical world. And they're arrows that live in this mathematical world, and the length of those arrows represent physical things. In this case, the length of that arrow represents the speed.
Okay, so it doesn't actually have to be the physical.
That's right. So it's not an actual length in. It's not a length like you would measure in meters.
Okay.
It's the length of that arrow in a mathematical world, kind of.
Okay. And I'm sorry, one more question.
Yeah.
For now. How do you know what that length is? Like in the equation, if it gives you multiple things, how do you know which one is talking about the vector?
So speed is always the length of velocity.
Okay.
So anytime you're given a speed, you know that's what you're going to use as the length to calculate the velocity components.
Okay. Thank you.
Sure. Can someone calculate those for me?
29.54. I got, oh, did you say 2.7? No, 54.
29.54. Then you did 3 times that.
Yeah, okay.
And then what's the other one?
Negative 5.21.
5.21. And that is units of meters per second. So VIX is 29.54. VIY is negative 5.21. And then do we know anything about the final velocity? Nope. But we're okay if we don't find out about that. So now we can think about what equations will work, and we're trying to come up with time final. And so I think what will work is PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So let's just check to make sure that this works. First, it has to have what we're looking for in it, and it does. It has TF. And now we're going to go through the rest of the variables and make sure they're all known. So PFY is known. You know what I should do? I should put this over here. So all the Y's are, so you can sort of eyeball what X's you know, what Y's you know. So, okay, PFY we know. PIY we know. VIY we know. AY we know. So this will work. Any questions about that reasoning? Yes?
I'm sorry. Are there ever going to be problems where we don't have to do the vector and you just know the velocity initial and the velocity final? Or
Yes.
Or velocity of x and
so-
velocity of y without it?
Yes. The next example we're going to do will be like that. But if you're ever given components, that's a velocity because speed isn't a vector. And if you're ever just given a positive, if you're ever just given a speed, then you know you have to use that speed to come up with velocity components.
Okay. And you said we're doing that in the next?
In the next example, we'll do one where you're given a velocity vector.
Thank you.
Okay, so 0 is equal to 3 plus 29.54 TF minus 4.905 TF squared. And we can use the quadratic formula for this. So there's A, there's B, and there's C. Anyone have any questions about how we know that needs the quadratic formula? So if you're trying to solve for a variable that's squared, and you also have just the variable by itself in a different term, then the quadratic formula is a good way to go. Yep. That is a mistake. Dang it. Okay, negative 5.21. Thank you. Okay, so can someone punch that into, someone who has that, the quadratic formula in your calculator, can you punch that in for me? I know some of you have it because I've programmed it in your calculators. What do you get? 0.04. That seems too small. And then you should get a positive and a negative. Negative 1.47. And then what was the other one? The same thing? 0.04? 0.41. Okay, that sounds more likely to me. 0.41 seconds. Anyone else get that? Okay. So we know that we're not going to deal with negative times, so we're going to take the positive one. Any other questions about that first part? So now we're going to go on to part B, and for that one we're trying to figure out how far away the ball hits the ground horizontally. So about those 4 things we have to choose at the beginning, is there any reason to change any of those? Nope. So we'll keep those all the same. And if we keep all of those the same, then all of the values we knew before stay the same. So we still know all the old ones. Those values don't change. And now we also know that TF is 0.41 seconds. And we want to calculate PFX. So I think this equation will work. PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So let's go through this and make sure that it works. It has PFX in it, the one that we're looking for. And now we'll go through the rest of them. Does it have PIX? Yes. Does it have VIX? Or I guess I sort of said that backwards. Now we're going through the equation looking for whether we know these other values. So we know PIX, we know VIX, we know TF, we know AX, so it works. So PFX is equal to 0 plus 29.54 times 0.41 plus AX is equal to 0, so this term goes away. It's an easy mistake to make to enter negative 9.81 for AX, but remember that's the Y component of the acceleration. The X component is always 0, or the horizontal component. So what's 29.54 times 0.41? 12.11 meters. Any questions about that one? Okay, so let me do another one that's, this is sort of similar to number 1 in 2D kinematics. So let's say at the starting instant, an object has a velocity vector of negative 15, positive 10 meters per second. It moves with a constant acceleration of 2, negative 4 meters per second squared for 2 seconds. So first, what's the object's velocity? I'll write that out. What's the object's velocity vector after this interval? And second, what's the displacement of the object over this interval? So notice we're going to do this problem without knowing anything about what this object represents. In number 1 in 2D kinematics, it says that it's a pool ball moving across a pool table, but we don't know what this is. We can just do it mathematically. One thing we do know is that this is not a free fall problem, because if you calculate the magnitude of the acceleration, it's not equal to 9.81. How do you calculate the magnitude of the acceleration? You'd go the other direction. So that's how you would go from the magnitude to calculating the components. In this case, you'd be going from the components to the magnitude, and you do that as the square root of 2 squared plus negative 4 squared. Remember that, the Pythagorean theorem? So it would be square root of 20. I don't know what that is. 4 point something. 4.47. So we know that's not free fall because the magnitude of acceleration in free fall is 9.81. Okay, so the first thing we have to do is make these 4 choices. Time equals 0, time final, origin location, and the coordinate system orientation. For time equals 0, we'll choose what this calls the starting instant. And then time final, that means we're actually given a value for time final. TF is equal to 2 seconds. For an origin location, well, we don't know anything physical about what this problem represents. So we're just going to put the origin at the object's location when time is equal to 0. Okay? And now the coordinate system. This is the thing that's different about this problem. When I first introduced the idea of position vectors and velocity vectors, I said that, or even when I first introduced vectors at all, I said before you can put a vector into components, you have to choose the coordinate system. Okay? Well, this is given with vector components. So if the components are given, that coordinate system has already been chosen for us. And there's nothing else we can do about that or have to do about that. So the coordinate system axes are already chosen. So the rule is once you have vector components, the directions of those coordinate axes have already been defined.
So it would be negative 15 and 10?
For the coordinate system?
Yeah.
What that means is if you have, so say this is the velocity vector, okay? We're given that the components of that velocity vector are negative 15 and 10. So the coordinate system orientation has to be chosen to make this true. So this vector has to be in the negative x direction and the positive y direction, which would be like, so the coordinate system would be something like this. So that coordinate system, you don't ever have numbers associated with the coordinate system. The coordinate system is the thing that lets you put numbers to vectors, lets you put components to vectors. Notice if we choose any other orientation of that coordinate system, you wouldn't get negative 15, positive 10 for the components of this vector. You don't have to do that. You don't have to draw anything in a problem like this. So I would say I've probably already talked about this more than is helpful. You know, I mean, I think the key thing is if you're given vector components, you know you don't have to choose a coordinate system. It's already been chosen for you, and the rest is just mathematical then. Okay. I'm going to erase this. Never think about that again. Okay, so now we'll list what we know and what we want. Do we know time final? Yep, that's given. Do we know the acceleration components?
No.
Those are given. 2, negative 4. So AX is 2, and AY is negative 4. Do we know the position at time equals 0? Well, we chose our origin to be with the object at time equals 0, so that means that PI is 0. That's a little annoying. P-I-Y. It sounds like a Wookiee has been captured. Question?
Why is PIY 02?
We chose the origin to be at the object's starting point. So that means that the object's starting point is at the origin, I guess, is the way to think about it. The origin is 0, 0, so both of those are 0. Do we know anything about P final? That's one of the things we're trying to calculate. First, let's just calculate the velocity vector. So no, we don't know the final position. Do we know the initial velocity?
Yes.
Yep, that's given. Yep. Do we know the final velocity? That's what we're trying to calculate. So I'm going to write both of these two up here. We'll just do them one after another. Okay, so to calculate VFX, I think we should be able to use this equation. VFX is what we want. VIX is known. AX is known. TF is known. So this will work. So VFX is equal to negative 15 plus 2 times 2 and so that is negative 11. And to calculate VFY, we'll use the y version of that equation. VFY is equal to VIY plus AY TF. So VFY is equal to 10 plus negative 4 times 2, and that is positive 2 meters per second. So then, since we're asked for the final velocity vector, we take these two components and put them in the vector form. So VF is equal to negative 11, positive 2 meters per second. Any questions about that part? For the second part, we're trying to figure out the displacement. Remember, the displacement is the position vector at the later instant minus the position vector at the earlier instant. We know the position vector at the earlier instant is just equal to 0, so all we're trying to figure out is the final position at the later instant. If we have that, then we're done. Those choices we'll keep those the same. There's no reason to change those. And that means that all the known values we had before are still the same. And now what we want to find is PFX and PFY. And we do know one more thing. Now we know, so we know all the old stuff, and we also know VFX and VFY. I don't think those are going to come up. So first, to calculate PFX, we can use this equation. So PFX is equal to, you can just go back to the old list and look up these values. PIX was equal to 0. VIX, what was that? Yeah, so minus 15. TF is 2 plus 1/2. AX is 2. And then TF is 2, and we're going to square that. So this is negative 30. This is 4. And so PFX is equal to negative 26 meters. And then PFY, we can use the equation that says PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. PIY was 0. What's VIY? Positive 10. 10 times 2 plus 1/2. And what was AY? Negative 4. Is that right? Negative 4 times 2 squared. So this one's 20. This one's negative 8. And so you get positive 12 meters. And then you can combine those into the final position vector. The x component is negative 26. The y component is positive 12. And then we were asked for the displacement. So the displacement here is the position at the later instant, that's our PF, minus the position at the earlier instant, PF is negative 2612. We're subtracting PI was 0, 0, 0. And so the displacement is the same as that final position vector, negative 26, positive 12. Any questions about that one? Yeah, it's mostly going to be free fall problems. There was only one example on the practice problems that was like this. So you should know how to do sort of a simple example like this, but mostly free fall. Any other questions? Or you want, otherwise I'll just introduce the new stuff. If any questions come up before Thursday, bring them to class, and I'd be happy to go through like exam type questions on Thursday. But otherwise, we'll just keep going with the new stuff. Okay? Yeah. Okay, so new topic. Kinetics of particles in 2D. So remember the thing that we talked about before was called kinematics. I don't know why they make these two words so similar. It seems like it makes it unnecessarily confusing. But kinematics describes the motion. And that means that it deals with quantities you could measure off of a video. And those quantities are time, position, velocity, and acceleration. Now going to kinetics, the idea of kinetics is that you combine kinematics with the causes of the motion. We haven't dealt with that yet. So the quantities, we're still going to see all of these old quantities. All of the kinematic quantities, plus two new ones. Force and mass. Before I can go into calculations and stuff, I have to introduce these two new quantities. I'm going to start with mass. That's the simpler one to describe. So now I'm going to introduce force and mass. So first, mass. Mass is a positive number that measures an object's resistance to being accelerated. Measures an object's resistance to acceleration. An object that's really easy to accelerate has a low mass. An object that's really hard to accelerate has a big mass. So for example, if we didn't have scales or anything, that's supposed to be a semi. Looks like some kind of animal. So if you have a semi going this way and a smart going this way, the reason this is really dangerous for the driver of the smart is when these two things collide, the thing with the much smaller mass is going to be accelerated a lot, whereas the truck is not going to be accelerated very much. In other words, the truck, these two things together are going to keep going at a velocity not so far from what the truck's velocity was before it started. So the truck is going to slow down a little from this collision. The smart car is going to turn all the way backwards. It's going to accelerate all the way back into the other direction. Okay? So the truck that has more mass won't be accelerated much, won't get much acceleration. The car that has less mass will be accelerated a lot. Okay, so that's what mass does. And it turns out that, like as you know, if you're on a planet, or really, actually, if you're near anything else that has mass, your mass correlates to a gravitational force. And so for us, we can measure our mass by getting on a scale. Okay, but getting on a scale depends. A scale working to measure your mass depends on there being gravity. And so this is sort of an interesting thing. So how would you measure mass if there was no gravity? That turns out to be an important question for astronauts because they're out where they can't feel any gravity. But maintaining their mass is a really important thing. They need to be measuring their mass accurately because you can lose bone density and you wouldn't know that that was happening until you got back to Earth and had major problems. So they really need an accurate way to measure mass. So how do they measure mass in a place with no gravity? You can't use a bathroom scale. Yep.
Well, like for horses, they take the measurements around different areas of their body, maybe.
Well, yeah, but bone density, you can't do that, and that's the main thing. So what they do has to do with this definition of what mass is. They put them on a thing that shakes them around, applies known forces to them, and measures how quickly they accelerate. They get on this thing that, I've never seen it, I'm only imagining it, you know. And by measuring how much they accelerate, this thing can measure their mass. Okay? So that's what we're used to thinking of mass as connected to the amount of weight you have, but the real definition of mass is it's big if it makes it hard to accelerate. It's small if the thing is easy to accelerate. The SI units for mass are kilograms. That's a little bit of a surprise because you would think the SI unit would be just grams without that prefix on it, but it's kilograms. That's just how it is. We don't get to decide that. Okay, so mass is a number, and it's always positive. Okay, so a number, a positive number, doesn't have any direction associated with it. A force is different. Force does have a direction associated with it, and so force is a vector. So a force is a vector that measures the intensity of push or pull on an object. The intensity of pushing or pulling on an object. Since it's a vector, force has direction. Mass doesn't. The SI units for force are kilograms times meters per second squared. Okay, it's this crazy combination of units. But since we're going to use force all the time, we're going to repackage this into its own unit. And so 1 kilogram meter per second squared is equal to 1 Newton. And we'll abbreviate that capital N. Okay, so what produces forces? In this class, there are a few other things that can produce forces that we're not going to deal with in this class. But in this class, there are only 2 things you have to worry about that produce forces. So there are only 2 sources for force on an object. The first one is weight. That's the force applied by gravity. And the second one is contact with another object. There can be other forces besides those, like electric fields. Electricity can produce forces. Magnetism can produce forces, but this is all we're going to do. And those aren't any harder to deal with. We're just not going to. Since force is a vector, we need to choose a coordinate system so we can express it as components. And we haven't seen this before, but now we're going to have to limit the coordinate systems that are allowable to us. Not all coordinate systems are allowable anymore. Okay, so in kinematics, we did say that there are rules for what a coordinate system is. The axes have to be perpendicular, and it has to be a rotated version of this, not a flipped version. But outside of that, the coordinate system could be doing anything we want, and the kinematics equations hold. Now we're going to be more restrictive. So in kinetics, coordinate systems must be inertial. And here are the two requirements for an inertial coordinate system. The first is that the origin can't be accelerating. And the second one is that the axes can't be rotating. Okay, so when you think of a coordinate system, think of a video camera. So think of a coordinate system as a video camera observing an object's motion. In order for this video camera to give adequate measurements the camera can't be accelerating. And it can't be rotating. Okay, so let me try to kind of illustrate that. I have a video queued up here. So I'm going to show a video of like something that looks odd. Okay, it's like a funny video on YouTube, but the reason it's funny is because it just looks odd. And it looks odd because it looks like physics are being violated. It doesn't look like it makes any sense with physics. The reason it doesn't look like the physics makes sense is because the video camera that's used to take it is accelerating. And that means that it looks like the laws of physics that we haven't talked about mathematically yet, but we all have experience with. It looks like they don't hold. Okay, so here we go. Have you seen this video before? It's funny because it looks like she gets hurt. Okay, so it looks like she levitates, right? Which we all know is not physically possible, right? The reason it looks like something happens that's not physically possible is because that camera is in that bus, which accelerates, hitting a big bump. And so based on what that camera sees, which is a coordinate system for our sort of intuitive understanding of physics, it looks like the laws of kinetics aren't holding. Okay, so anyways, that's all I'm going to say about inertial coordinate systems. But if you use a coordinate system that's not inertial to try to do physics calculations, your calculations are off. For the same reason that your sort of internal intuitive calculations of what should happen there were off because that camera was accelerating. In an inertial coordinate system, you can think of forces as being defined by this equation. And you've probably heard this equation mentioned before. Force vector is equal to the mass times the acceleration vector, F equals ma. This is Newton's second law. And this is the single most important equation in this class. And this, let me say a little bit about what each of these variables represent. So this F is the sum of all the force vectors acting on a chosen object. This m is the mass of the chosen object. And a is the acceleration of the chosen object. Anybody have any questions about anything yet? All right, so finally, that's sort of the end of my opening spiel about forces and Newton's second law. Now we're going to get to some calculations. Let me just say a couple more things, and then we'll stop for today. But the next thing we're going to do is, remember I said that there are two types of forces we're going to deal with. Forces applied by gravity, the weight, and forces applied by contact with other objects. The next thing we're going to do is use Newton's second law to determine the force applied to an object by gravity. And that force applied to objects by gravity is called the weight. Okay, any questions? All right, let's stop there.